On tonight's rivalry game, we have the Proton Hoopers versus the Polyballers. The Proton Hoopers are 30-4, and the Polyballers are 29-5. This is the game we've all been waiting for. We interviewed the Proton Hoopers this morning to get their insights. Let's do some pre-game scouting and take a glance at the Polyballers' game strategy. First, we'll get into their history. Polymers are large molecules composed of much smaller repeating units called monomers, bonded together. There are three different types of polymerization: free radical. Free radical polymerization includes an initiation step to form a radical, propagation to add the monomers together, and a termination to complete the mechanism. Anionic polymerization occurs through a nucleophilic attack on a monomer to form a stable carbanion, which continues to polymerize. Cationic polymerization includes the formation of a carbocation, which adds to electron-rich monomers to create a polymer. We need to determine which polymerization the polyballers will utilize in their game. Lastly, there are two major classes of synthetic polymers: chain growth and step growth. What does this mean?
First, we're going to look at chain growth polymerization, which happens only at the end of a chain. The end of this chain is called the growing end of a chain. Rapid addition of the monomers will occur here, one at a time, to the reactive intermediate without losing any of the molecules. Polymerization involves successive additions across the double bonds, where the monomers are typically alkenes. Next, we're going to look at step growth polymerization, which differs from chain growth in that it consists of two different monomers instead of just the one. Any two monomers with the right functionality can react with each other. Most polymers formed by step growth are condensation reactions, following the loss of a small molecule, often water. Common step growth polymer condensations include forming amides and esters. Let's apply our scout knowledge to the real thing.
For our real we are adhering heat transfer vinyl to a shirt. The shirt we chose is made out of cotton and recycled polyester. Polyester can trap heat and is lightweight as well as flexible, which is why we mainly see it used in sportswear. There are two types of polymers that can be used in heat transfer vinyl: polyurethane and polyvinyl chloride. Polyurethane is a block copolymer which contains urethane structural units. Its molecular structure consists of soft and hard segments, which we will show you later on whenever we draw out the chemical reaction. Polyvinyl chloride is one of the cheapest and most widely used plastics. It is not thermally stable at high temperatures and cools to a hard, rigid solid. For our project, we are using heat transfer vinyl thermoplastic polyurethane. Thermoplastic polyurethane is a versatile polymer that combines the elasticity of rubber and the processability of plastics. This means that it is flexible and durable with chemical resistance. It is thermally conductive, meaning it creates a good heat transfer source, and it is pliable when heated and then solidifies when it's cooled. Lastly, it is resistant to oils, grease, UV radiation, and many chemicals, which is why it's very good for practical wear and use.
Lastly, our thermoplastic polyurethane undergoes free radical polymerization. This polymerization happens during oxidative degradation. Let's take a look at the chemical reaction behind this. Here's the video of me drawing out the thermoplastic polyurethane that we are using in our heat transfer vinyl. This is the chemical reaction for it. Thermoplastic polyurethane undergoes a free radical polymerization during oxidative degradation. In short, this means that the thermoplastic is degrading and getting softer as the heat is applied. The thermoplastic then melts to the shirt and then solidifies and adheres to the shirt while cooling. Oxidative degradation is the chemical breakdown of materials. This happens primarily with polymers, plastics, and fluids. This happens when it is reacted with oxygen. It is often accelerated by heat, light, or stress. In our example, we are using heat. It involves free radical mechanisms that cleave molecular bonds. The cleavage of these bonds reduces material integrity and causes discoloration, surface cracking, or increased fluid viscosity. These are our sources that we used for this project. And now let's take a look at real life orgo and the real game that's happening tonight.
For this project, we not only wanted to explain verbally what was happening when t-shirts are made with heat transfer vinyl, but we also wanted to see for ourselves, so we decided to go to the Walk Knowledge Lab and use the Cricut machines there. We started by creating the design for the shirt. This design was etched onto the heat transfer vinyl that would be eventually adhered onto the shirt. This vinyl consists of a shiny side, that's the protective backing to be peeled off after applying heat, acting as a heat shield of sorts, and a matte side, which is the heat-activated material or the polyurethane as mentioned earlier. The Cricut cuts through the heat-activated material in order for the design to be easily transferred. After it was cut out, we peeled away the vinyl, leaving only our design and the protective backing. Now this is when the real chemistry comes in. We placed our design on the shirt and using a heat press melted the vinyl on. The heat had to be set at a lower temperature because not only is the heat transfer vinyl a polymer, but the shirt also contained polyester. Polyester is a thermoplastic that can melt or warp if heated too high, just the same way that heat transfer vinyl does. Because of its long chain-like structure, too much heat can cause the molecules to gain energy and disrupt the structure of the polymer. In our case, we wanted the vinyl to melt and warp, but not the shirt. The structure of the vinyl was created in such a way that it would soften at lower temperatures than the material it was being applied to. After heating our vinyl, we were able to peel back the protective backing and see the chemistry that happened right in front of us.
Thanks, Natalie, for that insight on the heat transfer vinyl in our project. Now let's get back to the game.
Welcome back to the biggest game of the semester. The proton hoopers and polyballers are tied with less than a minute to go. This has been the most exciting game that we've seen in a while. The polyballers have been absolutely stellar, adding monomers, completing condensations left and right. And on the other side, we have the proton hoopers. They haven't missed a jump all night. Their shifts have resulted in major resonance, major stability. They are very close to these polyball team tonight. With the clock winding down, this may be the Proton Hoopers' very last chance to solidify a win. The Proton Hooper star player Lewis brings the ball down the court. She faces a tough defense. But wait, what's happening? I think she's going to try to take it all the way. Something's going on with the polyballers' defense. Some sort of oxidative degradation is causing their defense to have some cracks. Lewis slips through, dodging monomers all the way. She shoots. She scores! The Proton Hoopers have done it. They've won the game. The polyballers just could not keep up tonight. Lewis, what a play. Can you give us some insight on what helped you guys come out on top tonight?
I mean, yeah, man, there's a lot to it. We focused on maintaining a stable environment with the team, and we really worked together as a team tonight. It was wonderful.
How much did scouting play a role in your preparation and getting ready for tonight's game?
Yeah, scouting was huge for sure. I mean, the main reason we won tonight was because of the scouting and all the knowledge and understanding that we had of the polyballers and all their plays. I mean, we had a lot of knowledge. Knowing about the free radical mechanism was really crucial. I mean, that's one of the reasons why I got them in that last play and breaking them down through their oxidative degradation. I mean, that's how I got that last shot, and really, that's the game winner for us.
Wow, I mean, just fantastic performance tonight from Lewis and the whole Proton Hoopers team. Any last words, Captain?
I mean, yeah, actually, I have a really big shout out. I think one of the main reasons we won and had success this season was because of our coach. Coach, we really couldn't have done it without you. We learned so much about all the teams, so much about the orgo and all of the presentations and everything that we did. I mean, we couldn't have done without you, Coach. We're so grateful.
Now that we just watched that exciting ending to the biggest game of the semester, let's do a little recap to summarize all of the information. Today, we have taken a deeper look at polymers and their real-life applications, such as fabric adhesive materials. We have looked at what a polymer is, the 3 different kinds of polymerization, and 2 major classes of synthetic polymers. We went in depth on the 2 different kinds of synthetic polymers, chain growth and step growth, and the 3 different types of polymerization, free radical, anionic, and cationic. We then learned about the 2 different kinds of heat transfer vinyls, polyurethane and polyvinyl chloride. Our project utilizes thermoplastic polyurethane, which undergoes a free radical polymerization mechanism. Recall that this chemical reaction took place when we used the heat press to adhere heat transfer vinyl to our cotton and polyester shirt. The blended fabric of the shirt is also made up of polymers, specifically polyester, with distinct properties, making the shirt soft, breathable, and durable. The unique polymers in the vinyl adhesive and in the shirt's fabric connect in a special way, bonding the two materials. The polymer reaction touched on a new topic of oxidative degradation that breaks down the polymer. With this being said, we hope that the next time you're getting ready for the day, you stop and wait a minute to think about the different types of polymers and mechanisms that are involved in making all of your clothes.